All right, so we are going to continue with section 5.4. So I already covered indefinite and definite integrals, a little bit of that. So this is all just a review. I'm trying to move through it quickly and not going into super strenuous detail just because you guys have seen it before. I just want it to be a review. So what the net change theorem is going to deal with, what we're going to consider first is let's think about the fundamental theorem of calculus. The second version of it. So if you need, I'm about to write it down, but you can go back and look in that section. I think it's beginning probably 5.3, 5.2 if I had to guess. So what this theorem says is, so let's suppose that we have a function f, capital F, and when I take capital F's derivative, I get little f of x. So what the fundamental theorem of calculus says is if I integrate, so let's integrate f of x dx, little f of x dx from a to b. This is going to be capital F of b minus capital F of a. And this is the fundamental theorem of calculus part 2 here. Now what the net change theorem is, I can use this relation right here up top, that capital F prime of x is equal to little f of x. If I plug that into the integral, I'm going to get the integral from a to b, capital F prime of x dx is equal to f of b minus f of a. And I have to assume that the normal things. And again, I'm not writing this all down because you've seen it. I have to assume that this function is continuous or piecewise continuous at least. And this is the net change theorem. What you have to remember here is capital F is the rate of change of, so capital F prime is the rate of change of F. And what this says is when I integrate the rate of change of capital F from a to b, all I have to do to figure out, or what that ends up being here, is the net change. So this is delta F. So all it ends up being is the change in F. And that's going to have some implications. We're going to see some examples. So I'm going to go ahead and click new whiteboard, and it's going to wipe the screen. I'm going to try, so I didn't do it with the first one, but after this one, I'll try saving my notes so you guys can have them if you want. I think it has pictures when I finish recording. So we'll give that a shot. So let's look at a couple of examples. So, why this is important. Is that we may need to find, we may need to find some quantity, but only have its derivative. So let me go back. So we may need to find, the change in some quantity. So the change in a quantity, but we only have information about its derivative. And what this net change theorem says is I can figure out what that change, sorry, I don't know why that did that. So what the net change theorem says is I can find that change by using the function's derivative. This is important, it might, trying to find the position of, so we're going to see this example later. It's a physics example. But, if I want to figure out, the displacement of something, so we'll define this, but the displacement is, how far something has gone away from you. And, it's hard to sit there and keep track of where this thing is at every second. but it might be easier to look at its velocity. And we're going to see that the position and velocity are related by a derivative. And this will allow us to find, the displacement, its change in displacement, only using its velocity. So only by knowing its derivative. We'll see an example of this. That's the example I picked for this. But let's look at so there's a bunch of examples in the book, and I'm not crazy about all of them. The first one is, so you have V of t is the volume of water in a reservoir at time t. And you're looking down a well and you're looking at this water level, and it might be really hard to figure out how deep the water is at any second. But it might be easier to look at how fast the water is draining from the well. So let's say V prime of t is the rate at which water enters or leaves the well. So it's the rate at which the volume is changing. So if I want to figure out, so this might be easier to measure. And if I wanted to determine the change in volume between 1 and 2 seconds, if I have V prime of t, I can just do this integral from 1 to 2, V prime of t dt. And this will just end up being, this is that volume. So this is going to be V of 2 minus V of 1. So the idea is, this V prime of t is something I might be given. I can integrate it and then do the evaluation and get, this new information about the change in volume between 1 and 2 seconds. And that's going to be important, when we talk about physics and things like that. So let's look at another example. Actually, let me get rid of that. We'll pull that up. Okay, so the next example. So I'm going to skip some of these because some of them aren't super enlightening and they're not very cool examples. So one thing that might be easy to determine, so this is a biology example. So it might be easy to determine the growth rate of a population. We'll call this dn dt. So this dn dt is the growth rate of a population. It might be the human race. It might be, some, I don't know, if you're a turkey farmer, I guess you could be interested in how that is changing. Turkeys don't, I guess, populate as fast as humans do. Well, maybe they do. I think there are more. I know there are more chickens in the world than there are humans, but anyway. So let's suppose that I'm given this function that tells me how this population's growth rate is changing. And what I can find out from this, so if I wanted to determine the change in population between T1 and T2, then what I'm going to do is, so the change in population is delta n. So what I can do is I can just integrate n prime of t dt. Oh, sorry. Touching buttons I'm not supposed to. From t1 to t2. This is going to be n of t1 minus n of t2. Again, I'm being very vague and ambiguous about what I'm given and what I'm not. Typically, what I'm given in the problem is it's easier to figure out these rates than it is to figure out the actual functions that describe these populations. So that branch of math actually you learn how to do in differential equations. But for now, instead of being able to figure out what these functions actually might be, we can figure out what the changes of these quantities are. So given the rate of change of a population, I can figure out the population change between two times just by integrating. Let's do one more example before we move on to an actual problem where I compute something. And this is geared more towards physics. So what I have is if I have displacement, I have a displacement s of t, so a function that describes how far something is away from me at any given time. Its velocity of, so let's do displacement given by s of t of a particle on the x-axis. Then the velocity of the particle. Velocity has units of meters per second, so s of t has units of distance, so then that's going to be the derivative of the displacement with respect to time. And if I want to determine, so this s of t is position. If I wanted to determine displacement, so how far something is from me, then I can do the integral from t1 to t2 ds dt. Sorry, I'm not going to write it like that because it's s prime of t dt. And so given the velocity, I can figure out the displacement by integrating and evaluating. Cool. So let's do a couple. I think we're just going to do one example and call it a day. Yeah, so we'll do one example with two parts and then call it a day. All right. So we have an example. So we have particle moving along x-axis with position given by with velocity. Yeah. So it's easier to measure velocities than it is to measure something's displacement at any position at any given time. So with velocity, v of t equal to t squared minus t minus 6. And part A is to find the displacement. Find displacement during 1 less than or equal to t less than or equal to 4. So if you look back at the previous page, we already saw that the displacement is given by the integral over the time, so between 1 and 4, s prime of t dt. And I already kind of talked about how position and velocity are related. So s is the position, s prime then, the derivative of position is velocity. So this is the integral between 1 and 4, v of t dt. Let's go ahead and plug in, we have a function for v of t. This is the integral between 1 and 4, t squared minus t minus 6 dt. Parentheses around it just so you know that all of this is being integrated. This dt also helps with that, but just to be doubly careful. And then we're going to integrate this function. So we're going to integrate it term by term. I'm going to do it quickly because, again, just a review. So t cubed over 3 minus t squared over 2 minus 6t. I'm evaluating that between 1 and 4. Okay, so let's go ahead and do this. So if I plug in 4 cubed, so I get 64 divided by 3 minus 16 over 2 minus 24. So this is what happens when I plug in 4 into the function here. Subtract off what I get when I plug in 1. So this is going to be minus 1/3 minus 1/2 minus 6. 64 over 3, I don't think simplifies. No. So we get 64 over 3 minus 8 minus 24 minus 1/3 plus 1/2 plus 6. And so you can do this. Well, apparently what you get with this is -9 over 2. So the displacement, of this thing, so how far it is away from the origin, going between these two times, is given, or is -9 over 2. Okay, so let's do the next part. Next part's a little different. We'll have to think about it. So find the distance traveled during this time period. Okay, so the way you need to think about this one is, if I think about, what this velocity, so this is time, and this is velocity, what this is going to look like is, I'm going to have some places where it's positive and negative, so on and so forth. I know our function doesn't really look like this. So these areas up here, we know have positive value when I integrate. These areas down here have negative value. So the idea behind the idea with this one is that, when I integrate this function, it might be positive, might be negative. But if I want to find, instead of, if I want, so this one, so the first one I want to find the displacement. This one I want to find the total distance traveled. And what you need to think about with this is, when I'm doing the integration, these two things are subtracted from each other. So they account for different things. So, if I go forward and then go back a little, those are going to add to, so when I add those together, I get, a number that's smaller than if I just add them together both positive. So what I actually want to do is I actually want to figure out, I want to make all of these numbers positive and just add them all together, and that'll be my total distance. I want to figure out how far I went, forward, add how far I went backwards, but without the minus sign, add how far I went forward, and add how far I went backwards without the minus sign. So what I'm really doing with that is I'm actually looking for this. And let me switch back to black. I'm actually looking for, I want to make this function totally positive. The way I can do that is by integrating the absolute value of v. Okay, so how does this help us? So what you need to know with this is, there is no, magic way of just putting this, these two lines around it and everything becomes positive. What we're going to do is we're going to find out where v is negative and make it positive. The way we're going to do this is we're going to figure out the zeros of v. So if you look back, v of t is t squared minus t minus 6. I'm going to figure out where this is equal to 0. And I want this to be equal to 0. So when I write this exclamation mark over something. That just means I want this to be 0 because I'm trying to figure something out. Okay, so if I go through and figure out where this is 0, this factors, I get t minus 3, t plus 2 is equal to 0. So this function goes to 0 at 3 and negative 2. So the reason I'm doing this is because I need to figure out where the function is negative, and the only time it can be negative is go from positive to negative is around 0. Okay, so you can think back to Calc 1. We have our sign chart. We're going to ignore the negative 2 root because, you know, that's not even in our interval. Our interval is 1 to 4. So I'm really only worried about this 3 here. So my interval is 1 to 4. You know, whatever happens, something happens at 3. So the function goes to 0 at 3. So I need to figure out where the function is positive and where the function is negative. So if I look back at my function here, so let me bring it over here. So we have v of t is equal to t squared minus t minus 6. I need to figure out if it's positive or negative between 1 and 3, so I can pick a point, any point I want between 1 and 3. If I do 2, I'm going to get 4 minus 2 minus 6, and this is less than 0. So I know my function is negative here. And I can do the same thing for, you know, a point between 3 and 4, and this is a little harder. But when you go through and do this, there are some tricks you can do to do this. You're going to figure out this is positive here. So what I'm going to do now is I'm going to break this integral. So I'm going to break this integral. So the integral from 1 to 4, v of t dt. So I'm going to break it into the parts where it's positive so let me put the absolute value signs. And so where it's negative and where it's positive. So for this first one here, we know v of t is negative. So I look up at my sign chart here, and I already went and saw that this is negative. So how does the absolute value sign, how does the absolute value function deal with things that are negative to make them positive? Well, think back to its definition. Absolute value makes negative things positive by sticking a minus sign in front of them. So if I stick a minus sign in front of this integral, this is just v of t dt. And then this, the second absolute value sign for this one here, v of t is already positive, so I don't need to do anything to it. This is the integral from 3 to 4, v of t dt. And because I'm using up a lot of time here, I'm not going to do these integrals. I'm going to leave them to you to do. So when I do this, I end up getting 61 over 6. And there's a decimal approximation. This is 10.17 meters. So you can look back if you need to figure out what the antiderivative for v of t is. I did it in the first part, but one thing you should notice is that the displacement between times 1 and 4 is less than the total distance traveled, and that's going to be something that's pretty normal. I think that holds always true. It's always less than or equal to. But yeah, so I'm gonna stop the lecture here. This is the end of section 5.4. My plan is to do these lectures, throw a couple examples in, but I'll also put up a video or two for each section where I work through some example or work through some more examples, just so you have more than what's in the book. All right.